Okay, so welcome to the course on analog and digital electronics. See, in the previous sessions of analog and digital electronics, we have started with the linear applications of operational amplifiers. In that, we have seen ideal inverting and ideal non-inverting amplifier, and after that, we have seen practical inverting amplifier. So, we have seen the importance of providing feedback, negative feedback to the amplifier, right? So, we will see some enhancement in the values of closed loop voltage gain, input resistances, output resistances, bandwidth, as well as total output offset voltage, right? And we have seen this, we have verified this using one simple example of inverting amplifier. Now in today's session we are going to discuss about practical non-inverting amplifier. Okay, so like we have done analysis in case of inverting amplifier, we will also try to do the analysis of non-inverting amplifier and try to find out these parameters: closed loop voltage gain, input output resistance with feedback, bandwidth with feedback, and what should be the amount of total output offset voltage with feedback. Okay, so talking about non-inverting amplifier, is similar to the practical inverting amplifier. The parameters of practical non-inverting amplifiers are different than the parameters of the ideal non-inverting amplifier. Okay, so we will see the effect of negative feedback on the various parameters of this practical non-inverting amplifier. Okay, so first of all we will require some circuitry for non-inverting amplifier, right? Now as we have discussed, whenever we talk about the non-inverting amplifier, that means we are providing the supply or voltage signal to non-inverting terminal over here. Okay, so we have applied some voltage, say V in, to the non-inverting terminal of the amplifier. Okay, let us say this is my terminal B and here is my terminal A. Okay, and inverting terminal of the amplifier is grounded. Okay, these are usual resistances R1. Here is my resistance, feedback resistance RF, right? And this will provide us some open loop gain, say AOL. It is supplied by dual supply, positive VCC and negative VEE. And at this terminal, say pin number 6 of IC 741, we will get some output voltage across this load resistance. Okay, so this will be the output voltage, right? So this is the simple circuit diagram of practical non-inverting amplifier. Now talking about the current, see, the amplifier circuit will amplify the difference between the two input signals. Okay, so here between these two terminals we will find some difference voltage VD, and this difference voltage VD gets amplified. Okay, now it is non-inverting amplifier, so we know the equation. In case of ideal non-inverting amplifier, it was 1 plus RF by R1 times V in. Okay, that was the equation. Okay, so according to this equation, if we take the ratio of output voltage by input voltage, V0 by V in, it is called gain A, and it comes around 1 plus RF by R1. And this is the reason why we have concluded that in case of non-inverting amplifier, the gain will always be greater than or equal to 1. Okay, now consider the current. We have applied certain amount of voltage V in to this terminal. Okay, and output voltage will be generated. So the current flow in this case will be in this direction. Let us say this current be IF. Okay, so this is the direction of current which is flowing in this particular direction, right? And at terminal B we are getting some voltage V1, and at terminal A we are getting some voltage V2. Okay, So this V1 minus V2 will give us the difference voltage VD. Okay. Now talking about the operation of this circuit, see, op-amp always amplifies the difference input voltage VD, and this difference voltage is the difference between the voltages V in and VF. Okay, where what is VF? VF is the feedback voltage. You can see the voltage drop across this RF is directly connected to terminal A. So this terminal A will be at potential VF and terminal B is at potential V in. Okay, so the difference between V in and VF will be our difference voltage. Okay, and this feedback voltage will is opposes the input voltage. Okay, it will be 180-degree out of phase with respect to the input, and that is seen. See, the direction of this voltage is in this particular direction, while we are getting over here. Let me say this is my positive, this is my negative terminal. Okay, so talking about this voltage V in and voltage VF. Okay, V in and VF, they are 180-degree out of phase with each other. Okay, and that is the reason why we call it a negative feedback. Okay, so whenever the difference voltage, two difference voltages are of 180-degree out of phase, at that time you may consider that we are available with negative feedback. Okay, and this practical non-inverting amplifier is also known as voltage series feedback amplifier. Okay, it is a non-inverting amplifier or voltage series feedback amplifier. Now why it is called so? For that, again we will consider the simple circuit which we have already considered in case of inverting amplifiers also. Okay, so inverting amplifier was known as voltage shunt feedback amplifier, while non-inverting amplifier is known as voltage series feedback amplifier. Okay, so let us understand why it is called. Okay, see, this is my non-inverting terminal, this is my inverting terminal. Okay, so with inverting terminal we have this feedback resistance RF, sorry, okay, which is connected in this fashion. Right. Now let me connect R1 over here. Okay, this is the connection of R1 and it is grounded. Okay. R1 RF. Okay, and then we will have load resistance over here. Okay. So this is our load resistance, and to the inverting terminal we are providing some signal source, okay, which is V in, okay, and that is directly connected to output terminal RL. Okay, now positive supply voltage and negative supply voltage will be there. Okay. So this is one typical figure. Okay, here this is my potential V1, this is my potential V2, and there is a difference voltage VD which is available over here. If you see these two resistances, if I talk about this block, okay, this is nothing but the feedback circuit. and this typical configuration is known as voltage series feedback amplifier. Okay. So inverting amplifier can be called as voltage shunt feedback amplifier, and non-inverting amplifier is also known as voltage series feedback amplifier. So this is our typical circuit diagram. Okay. Now for this circuit diagram, let us try to derive the closed loop voltage gain. Okay. That is our first parameter which we need to know. Okay. What are the controlling parameter of this closed loop voltage gain? That is important. Again, when we talk about the voltage, finding out the voltage gain, that means we are about to finding out the ratio of output voltage to the input voltage. Okay, and this output voltage to the input voltage is nothing but the gain of the amplifier. Okay, so we'll try to relate these two parameters, the input voltage as well as output voltage in this particular case. Okay, so ultimately my closed loop voltage gain is nothing but the ratio of these two parameters. Okay, and we'll try to find out this. Okay, so now talking about the output voltage V0. See, output voltage V0 is nothing but the AOL times difference voltage, that is VD. Okay, so we have this equation. V0 is equal to AOL times VD. Okay, what is VD? VD is difference between two terminal voltages, that is V1 minus V2. Okay, where V1 is input and V2 is the feedback voltage which is available across this resistance RF. Okay, now see, I'm talking about this VF. Okay, where, okay, I just let me write down over here. So V1 is equal to V in and V2 is equal to Vf across R1. Okay, so now this is not the only Vf. If you wish to find out the magnitude of Vf, then let us go back to this circuit diagram. If you see, there are two resistances connected in parallel, okay, R1 and Rf, and we are measuring the voltage over here. Okay, so if I am talking about the Vf, then Vf will be the voltage across this resistance R1. Okay, so using voltage divider rule, we will be able to find out this Vf. Okay, so now Vf will be equal to R1 divided by R1 plus Rf into V0. Okay, so using voltage divider rule, Vf is given by R1 upon R1 plus Rf times V0. Okay, so this is the equation. We will call this as equation number 3. Okay, and just put this equation number 3 into equation number 2. Okay, so we are putting the value of V2 which is equal to Vf. So V0 will be equal to A0 AL times V1 is equal to V in and Vf is equal to R1 times V0 divided by R1 plus Rf. Just simplify the thing. We will have A0L times V in minus R1 AOL V0 divided by R1 plus Rf. Okay. So here V0 is there, and if you see this equation, then in the second term we are available with V0. Okay, so the entire second term can be brought to the left hand side of the equation, and we will take V0 common parameter. So my equation will be V0 into 1 plus R1 times AOL divided by R1 plus RF, that is equal to AOL times V in. Okay, so here you can see I am available with V in, and on the left hand side of the equation we are available with V0. Just take the ratio of this V0 and V in. That is what we got, closed loop gain ACL. Okay, so closed loop gain is equal to V0 by V in, and that is equal to AOL into R1 plus RF. I am taking LCM, right, on the left hand side, such that my equation will become R1 plus RF plus R1 times AOL. Okay, so this is the equation of our interest. Okay, in case of practical non-inverting amplifier, this equation gives the closed loop voltage gain. Okay, and this is called exact equation, the exact expression for the closed loop gain. Okay, now talking about the ideality, see, we do know that ideally out voltage gain is equal to 1 plus RF by R1. Okay, now let us confirm this particular thing. See, ideally what happens, talking about the open loop gain, ideally AOL is very large and it is tending to infinity. So what will happen to this parameter, AOL times R1? Okay, AOL times R1 will be very much greater than R1 plus RF. Okay, so if you neglect this term R1 plus RF, I am talking about this. If you neglect this term, then what is going to happen? Now my denominator of this equation becomes very large. Okay, so what we will get is, we will get this equation ACL is equal to 1 plus RF by R1. Okay, this AOL will get cancelled out and we will be left with R1 plus RF divided by R1, that is equal to 1 plus R1 by RF by R1, and this is the ideal case that we already know. Okay, so this result is derived for the ideal non-inverting amplifier. Already we have derived it. Now this is the closed loop voltage gain which is provided by this output non-inverting amplifier. Now let us try to derive the input and output resistances with feedback. Okay, so what is the difference? Ideally the input resistance must be very much high. Okay, and let us see the effect of providing feedback to the amplifier. Okay, so now we will try to derive the equation for input resistance with feedback. Okay, so to analyze the effect of feedback on the input resistance, let us try to obtain the non-inverting amplifier circuit using the equivalent circuit of the op amp, just we have done in case of inverting amplifier. Okay, so we will try to draw the equivalent circuit of the operational amplifier, and then we will try to derive the equation of input resistance. Okay, so we have two terminals, one is the non-inverting terminal and another one is the inverting terminal. Okay, and in between we will have some input resistance, let us say R in. Okay, this is the internal part, the internal part of the triangle. Okay, so let me show this with the internal part like this. Okay, this is my operational amplifier, and between two terminals I'm getting this. Okay, let us say this is my non-inverting terminal and this one is inverting terminal. Okay, so here we will have terminal voltage is V1 and terminal voltage is V2. Okay, now non-inverting terminal is provided with the supply voltage. Okay, so let us have a signal voltage connected to non-inverting terminal of the amplifier and then it is grounded. Okay. So this is my supply voltage V in, which will produce some current, input current, let us say I in. Okay, then there will be a difference voltage VD, a difference voltage VD over here. Talking about the inverting terminal. Okay, so to the inverting terminal we are providing feedback resistance and resistance R1 is also connected and it is grounded like this. Okay, and then we will have this feedback resistance in this manner. Okay, now talking about the output side. Okay, so whatever difference voltage we are providing, output will be AOL times this difference voltage. Okay, so here we can assume one voltage source which is equal to AOL times VD. Okay, and this voltage source is grounded like this. Okay, and to the voltage source there is one output resistance connected in this particular manner, and this is my output pin where we are measuring output voltage V0. Okay, and feedback resistance is connected in this fashion. Okay, so we are measuring output voltage across this load resistance RL. Okay, so this you can consider a simple circuit, equivalent circuit. Okay, this is the voltage drop across R0. Yes, all the parameters are considered. Okay, so this is my input resistance R in. Okay, and this is with feedback. Okay, so now we are interested in finding out these values of R in. Okay, there will be a voltage VF across this. Okay, now here this R in is the input resistance of the op amp without feedback, and let us say we wish to find out R in F, that is the input resistance with feedback. Okay, so the input resistance with feedback is nothing but the ratio of input voltage V in and input current I in. Okay, the input resistance with feedback, let us say input resistance with feedback is defined as the ratio of the input voltage V in, input voltage V in and input current I in. Okay, so ultimately we need to find out this particular ratio. Okay, and that is what our input resistance is. Okay, this. Right. So now let us come back to this current. See, I in. What is I in? I in is the current which is flowing from this supply voltage V in and through R in it is entering to the operational amplifier. Okay, so I in is nothing but the ratio of this voltage across this Rin. And what is the voltage across Rin? It is the difference voltage Vd. Okay, so Vd by Rin will be my In. Okay, so let us write down this. Now we have In equal to difference voltage divided by input resistance without feedback. Okay, therefore input resistance with feedback will be equal to Vin divided by Vd divided by In. Okay, now let us try to find out the equation for Vd. Okay, we know the equation which is relating Vd. It is equation of output voltage. Okay, so V0 is equal to AOL times Vd. Therefore Vd will be equal to V0 divided by open loop gain. Okay, and we also know from the block diagram, okay, if you consider the block diagram, then we know that V0 by Vin is equal to AOL times 1 plus AOL B. Okay, where B was R1 upon R1 plus RF, that is equal to, here B is equal to R1 upon R1 plus RF. Okay, it is nothing but the feedback part gain. Okay, so V in now will be equal to V0 into 1 plus AOL times B divided by AOL. So this equation of Vd and Vin, just we'll substitute these two equations in equation of R in F. Okay, so what will happen now? Therefore R in F will be equal to V0 plus into 1 plus AOL times B divided by AOL. This is the equation representing Vin divided by Vd by In. What is Vd? Vd is V0 by AOL. So Vd is V0 by AOL into Rin. Okay, so this is our equation. Okay, now simplify this equation. We will get Rin is equal to Rin into 1 plus AOL B. This is the amount of input resistance with feedback in case of non-inverting amplifier. Okay, so you can see the input resistance with feedback is 1 plus AOL times AOLB times that without feedback. Okay, Rin represents the resistance without feedback and RINF represents the resistance with feedback. Okay, so you can see we have improved the value of input resistance, and that is what we needed. Okay, we should have very large amount of input resistance to avoid the load effect of loading at the input terminals of the operational amplifier, and that is what we get when we providing negative feedback to the non-inverting amplifier. Okay, so this is advantageous. Providing feedback in case of non-inverting amplifier is also advantageous like in case of inverting amplifier. Okay, now let us consider another parameter, which is output resistance. Okay, so output resistance without feedback we know is R0, and now let us try to find out the output resistance of non-inverting amplifier with feedback. Okay, now whenever we are providing the feedback, what should happen to the value of output resistance? It should decrease by certain amount. Okay, because if we talk about the IC741, then it will give us 75 ohm resistance at the output side. Okay, so if we provide the feedback, now this 75 ohms should be reduced, then and then we will get some benefit, because ideally speaking the value of output resistance should be equal to 0. Okay, but practically this is not possible. but definitely we can minimize that particular value. Okay, so let us try to find out the output resistance. See, similar to inverting amplifier, the output resistance can be obtained by using Thevenin's theorem for the dependent sources. Okay, so what we will do, we will replace input voltage source by short circuit, that is 0 volt, and we will keep this AOL times VD. This is our dependent voltage source. Okay, let us go back to the equivalent circuit. So I'm talking about this source. Okay, this is my independent source which needs to be replaced by short circuit. So now potential at V1 will be equal to 0, and this is my dependent source. Okay, so we will keep this dependent source as it is, and then we will apply some voltage V0 to the circuit, which will force some current I0 into the circuit. Okay, and this output resistance is nothing but the ratio of this applied voltage V0 and the resulting current I0. Okay, so we'll try to draw the Thevenin's equivalent circuit in this case, and we will try to find out the ratio. Okay, so ultimately we have this output resistance with feedback is nothing but the ratio of V0 by I0. Okay. Now we have this case. Okay, this is my input resistance. Here we have dependent voltage source AOL times VD, and this is my output resistance R0 without feedback. Now to the non-inverting terminal, we have provided one voltage source. Okay, so here that was a voltage source. Now this voltage source is replaced by a short circuit. Okay, we can say V in replaced by 0. Okay, and then inverting terminal. So with inverting terminal we have resistance R1 and feedback resistance RF, okay, which are connected to output terminal over here. Okay. Let me try to represent our symbolic representation of op-amp like this. Okay, and there will be positive supply voltage plus VCC and negative supply voltage minus VEE. Okay, so this is my non-inverting terminal. This one is inverting terminal. This is terminal A. This one is terminal B. In between, we will have difference voltage VD. Right. So this is potential VA, which will be equal to V1, and potential VB, that is equal to V2. Now this is what we have done. Now what we are doing, we are providing some voltage, we are applying some voltage V0 to the circuit. Okay, so let us say here we are applying this voltage V0, which will force some current I0 into the circuit. Okay, so this I0 is forced into it. Now we have this terminal, let us say this terminal is C. So as you can see, this current I0 gets divided into two parts. Some part of current, let us say I0, flows into this way, and some part of current, let us say IB, is flowing through this feedback resistance is RF and forward resistance R1. Okay, this resistance is having a voltage drop of VF. Okay, so if we look back, from this way, if we look back from this way, then it will give us the value of output resistance with feedback. Okay, so let us try to find out this ratio V0 by I0 by simply applying Kirchhoff's current law, because ultimately we are interested in finding out the magnitude, the equation pertaining to I0, okay, as well as V0. Okay, so to find out the unknown voltage, we will apply KCL, and KCL needs to be applied at node C. Okay, so applying KCL, remember always KCL is applied when you want to find out the unknown voltages, and KVL can be applied when you want to find out unknown currents. Okay, so application of KCL at node C will give us this equation: IA plus IB is equal to I0. Okay, now we have this equation. See, I am talking about this resistances R in over here. Oh, sorry, this is my R out, R0. Okay, here is R in. Okay, so if you see this resistance R in, okay, it is connected with this parallel combination of R1 and RF. Okay, so this combined resistance of input side will be very much large compared to this output resistance. Okay, as we know, R in, okay, just we have calculated the value of R in over here. It is very much large, right? So if we compare this value with the output resistance R0, then R0 will be very much small. Okay, so we have this case, but we have R in which is connected in parallel with R1 plus RF, and it is very much greater than R0. Okay, this is because Rin is very high and R0 is very low, and hence resistance offered to the current IB, resistance offered to the current IB is very high compared to the resistance offered to current IA. Okay, so if we talk about the magnitude of this IA and IB, then IB will be very much less than IA. Okay, here IB is very much less than IA. So ultimately we can say I0 is approximately equal to IA only. Okay, so one can say the entire amount of current which is caused by this voltage source V0 is flowing in this particular direction. Okay, so now we know that the entire current I0 is flowing through this resistor, output resistance R0, and this dependent voltage source, and finally it is grounded. Okay, so if we wish to find out this magnitude of current, then we need to apply KVL to this output loop. Okay, so applying Kirchhoff's voltage law to the output loop, we will get this equation: V0 minus drop across output resistance, which is equal to I0 minus voltage source is A0L times Vd, and that is equal to 0. Okay, so this is a equation. Now from this equation we can find out the value of I0. Okay, so I0 is equal to V0 minus AOL times Vd divided by R0. Okay, let us give this equation number 4. Okay, so I0 is known to us. Now let us try to find out the value of the difference between difference voltage Vd. Okay, in this case. Okay, so if we come back over here, you can see the drop across the resistance R1 is Vf. Okay, so that Vf will appear at this terminal V2, right? So at V2 we have Vb and that is equal to Vf, that is what we know. So let us try to find out this particular thing. Okay, we are talking about the equation of Vd, right? So the drop across the drop across the resistance R1, drop across the resistance R1 is Vf. Okay, so difference voltage Vd is equal to V1 minus V2, which is equal to Va minus Vb, right? Now what is Va? Va is replaced by short circuit. Okay, so the Va terminal will be at zero potential and Vb terminal is at Vf potential. So just put these values. So we will get Vd is equal to 0 minus Vf, and that is equal to minus Vf. Okay, so difference voltage is nothing but minus Vf. But what is the magnitude of Vf? Okay, if you see the magnitude of Vf over here, okay, so this is the Vf, and you can see, you can easily find out the Vf by applying voltage divider rule. So by voltage divider rule, we have Vf is equal to R1 divided by R1 plus Rf into V0. Okay, if you see this equation, R1 divided by R1 plus Rf, what it is? It is feedback gain, feedback path gain, that is B. Okay, so Vf is nothing but B times V0. Okay, and what is Vf? Vf is equal to Vd. Therefore Vd is equal to minus B times V0. Okay, let us say this equation be equation number 6 and this being equation number 7. Okay, so putting this in equation of I0. Okay, now we have value of Vd. Okay, so just put the value of Vd in this equation of I0. So we will get the value of I0, which is equal to V0 minus AOL times Vd, but Vd is minus B V0 divided by R0. Okay, so that is equal to V0 will get common term into 1 plus AOL times B divided by R0. Okay, let us call this as equation number 8. So, okay, so equation 8 represents I0. Okay, now what is our ROF? Output resistance with feedback is nothing but the ratio of V0 by I0. Okay, so put this value V0 divided by V0 into 1 plus AOL times B divided by R0. V0 will get cancelled out and we will get this equation R0 divided by 1 plus AOL times B. Okay, so this is the value of resistance with feedback. Okay, and as you can see, this term 1 plus AOL times B is in denominator. Okay, so increasing this term, by changing this term, by increasing the denominator term, we will be able to decrease the value of feedback output resistance with feedback. Okay, so here the output resistance is 1 by 1 over 1 plus AOL times the output resistance of the op amp. Okay, this is the same result which we have derived earlier in case of inverting amplifier, right? Okay, so here also we can assume that we are reducing the value of output resistance with feedback. Okay, so negative feedback here also help us, it is advantageous. Okay. Now talking about the bandwidth, the frequency range. Okay, what happens to bandwidth with feedback? Okay, we'll go through this also. Okay, so in case of operational amplifier, see the frequency at which the gain is equal to 1, it is called unity gain bandwidth. Okay, we have seen this definition. Unity gain bandwidth, UGB. What is it? It is nothing but the frequency at which the gain equals to 1. The gain equals to 1. Okay, so for operational amplifier having single break frequency say f0, the gain bandwidth product will be equal to constant and it is equal to UGB. Okay, so unity gain bandwidth is equal to AOL times single break frequency, that is f0. Okay, here f0 is nothing but the bandwidth without feedback, or it is also known as f0 is, one can say, single break frequency or bandwidth without feedback. Okay, and also we know that unity gain bandwidth is closed loop gain times the bandwidth with feedback. Okay, this equation is also true. Here ff is equal to bandwidth with feedback. Okay, so we can compare these two. Okay, both are unity gain bandwidth. Okay, so 1 is equal to 2. That is the reason why we can write down AOL times f0 is equal to ACL times ff. Okay, so the closed loop voltage gain we know is, okay, we already have derived the equation of closed loop voltage gain. It is equal to A0L times 1 plus A0LB. Okay, therefore the bandwidth with frequency is now given by A0L upon 1 plus A0LB into f0. Okay, so simplifying the terms, we will get ff is equal to 1 plus A0L times B into f0. Okay, so this is my bandwidth with feedback, and as you can see, bandwidth with feedback increases by this much amount. Okay, 1 plus AOL times B. Okay, so bandwidth of non-inverting amplifier with feedback is equal to 1 plus AOLB times the bandwidth without feedback. Okay, so again we have disadvantage, we are increasing the range of frequency for linear operation of operational amplifier. Okay, now let us try to analyze the final parameter, which is total output offset voltage. Okay, so whenever we are providing feedback to the non-inverting amplifier, at that time what will happen to total output offset voltage with feedback. Okay, what we know about output offset voltage is, it is the voltage available at the output when input is 0, And what is the reason? Because of the input offset voltage and input offset current. Okay, so this voltage is the function of gain of the operational amplifier, and as gain reduces from open loop gain to AOL by 1 plus AOLB, the output offset voltage also reduces by this factor. Okay, 1 by 1 over 1 plus AOL times B. Okay, so VOOS is equal to, oh sorry, with feedback is equal to output offset voltage divided by 1 plus AOL times B. Okay, now what is output offset voltage? Output offset voltage is equal to either positive or negative saturation voltage. Okay, so here output offset voltage is plus or minus V saturation voltage. So ultimately output offset voltage with feedback is nothing but plus or minus saturation voltage divided by 1 plus AOL times B. Okay. So this is the total output offset voltage with feedback. Okay, so here AOL represents open loop gain and B represents feedback part gain, which is equal to R1 upon R1 plus RF. Okay, so this is what we get. Okay, now let us have one simple example to consider this effect. Okay, see, we have been given a non-inverting amplifier. Okay, so for a non-inverting amplifier, R1 is given to you 1 kilo ohm and RF is given to you 10 kilo ohm. Okay, and other parameters are, say, open loop gain AOL equal to 2 into 10 raised to 5, input resistance Rin equal to 2 mega ohm, output resistance R0 equal to 75 ohm, single break frequency, that is F0, is equal to 5 hertz. It is also known as bandwidth without feedback, and supply voltage Vs is equal to plus or minus 12 volt. Okay, these are the parameters given to you. Now what you need to do is you need to calculate closed loop voltage gain then input resistance, output resistance, and bandwidth with feedback. Okay, so whatever equations we have derived in this particular session, you all need to apply these expressions. Okay, remaining parameters which you will require for calculating the gain, input resistance, output resistance, and bandwidth are provided to you. Just we need to apply equations. Okay, so firstly we will try to find out the value of B, which is equal to R1 up 1 R1 plus RF. This is nothing but the feedback part gain. Okay, this is our feedback part gain. Okay, then if you wish to find out the closed loop gain, then it is given by AOL divided by 1 plus AOL times B. Okay, if you wish to find out the input resistance with feedback, then it is 1 plus AOLB times Rin. If you wish to find out output resistance with feedback, then it is 1 over 1 plus AOLB times output resistance without feedback, that is R0. And if you wish to find out the bandwidth with feedback, then it is also 1 plus AOLB times single break frequency or bandwidth without feedback. Okay, so on application of this derived expressions, we will be able to find out all the parameters which is required for this typical example. Okay, so this will be your homework. Just you need to find out all the parameters, okay, and tell me the answer in the next lecture. Okay, so this is all about the practical non-inverting amplifier. Okay, so we have completed the practical inverting and non-inverting circuits. Now you will be able to do the comparison of these two typical circuits, which is used very widely, right? Okay, so this is the end of first part of the linear applications of operational amplifier. See, today I will plot one assignment which is pertaining to some examples based on what we have done so far. Okay, so just try to solve all the example and just take the photocopy of this and upload it in as a reply to this particular assignment. Okay, the example assignments will be provided to you. So within a week, you need to reply with the answers. Okay, we will stop here for today. In the next lecture, we will continue with the linear applications of operational amplifiers. Okay, if you have any questions, then you are free to ask.